So today we are beginning a new lecture on our helicopter dynamics course. Today we are going to discuss forced vibration and the concept of resonance, which is very important for vibratory motion. This is lecture 10. I'm Dr. Anjan Ganguly. So in the previous lecture on the spring mass damper system and before that on the spring mass system, we basically neglected forcing. We assumed that there is no external forcing and this is known as free vibration. So here the system is basically pulled from its baseline position and then released and it moves on its own. Now free vibration gives you some basic ideas about some internal characteristics of the vibratory system, such as its natural frequency, its damped natural frequency, its response, and so on. Now in most real systems there is some external forcing which is present and acts on the structure or the system. So this external forcing has a huge impact on the behavior of the system, and today we are going to look at a model about how to study such behavior. So a simple forcing model which lets us get a lot of good insights into vibration is the simple model given here, that is F equals F naught, which is a constant, into sine of the forcing frequency into time. So remember that this forcing frequency is different from the natural frequency of the system. That is why we are not putting the subscript n here. That's the big difference. So let's go back to our spring mass damper system. So here we have our mass suspended from a spring. We have our dashboard damper, and then we have now created a forcing function here which is applied on this particular mass. Now this is a harmonic forcing because again we are using a sinusoidal type of forcing here. Now the next thing we do is we look at the free body diagram for this mass. Now if this mass is moving in this direction, x is, we define x as this direction from its mean position, then the restoring forces are going to be kx and cx dot, and also you are going to have mx double dot in the reverse direction of this displacement x. And now we have this extra forcing here, which is the applied external forcing. So this is new to this system here. So our equation of motion would be mx double dot plus cx dot plus kx is f0 sine of omega t. So that's our equation of motion. And that's the equation I write here. This is a good looking equation. You have the equation we had in our previous lecture, and now you have the extra forcing term here. Now if you go back to the theory of differential equations, whenever you have a equation of this form, it will have two solutions. One is a complementary function which is obtained by setting the forcing to 0 or the right hand side to 0, and second part of the solution is the particular solution, and that is obtained by keeping this particular part. So essentially this also has these two type of solutions. Now if we look at the first part of the solution, that is the solution of the homogeneous equation. So that would be the equation mx double dot plus cx dot plus kx equal to 0, and we have already discussed this solution in the previous lecture. So if you do not recall it, you can go and review that, but at the end of this lecture we are going to put that solution also. So we are going to concentrate on the second part of the solution, which is the particular integral. Now this second part of the solution, we have to think in physical terms, and what we will realize is that if we are forcing with this particular frequency, then after some point it's very likely that the system is going to vibrate with the same frequency, that is the forcing frequency, and we will assume that some phase difference is brought in because of the physics of the system. So essentially this is the solution we presume, and after presuming this solution we substitute it back into this differential equation here, and then we balance out the different terms which come out in terms of the sinusoids. Now, once you do that and you find the coefficients, you get x as this value here, and you get phi as this value here. So once you have x and phi, your solution as far as the particular integral is concerned is essentially obtained. Now this is largely an exercise in trigonometry, and you can do it in your free time. So we are going to now look at these two, further simplify it, and extract some physical reasoning out of these two equations. So if we look at these two equations, they can be expressed in a better form by using some normalized parameters or non-dimensional parameters. So what we do is we divide this denominator term here by k throughout. And if we do that, then here we would get this term here, which is the natural frequency square. Now, as far as this term here is concerned, here again, if we divide by k and consider the fact that c is given by this equation from our previous definition of the damping ratio itself, then we get this term here. Similarly, we can do the exercise for phi here. We divide the denominator by k, that gives us this term. We divide the numerator by k, that gives us this term here. Now, the advantage of expressing the amplitude and phase in this manner is that we have normalized terms here, or non-dimensional terms. So essentially you have a frequency divided by a frequency. Zeta is of course c divided by cc, so it is a non-dimensional term. So now if you look at this term, a very interesting fact will come to light. You can see that at the point when the forcing frequency is equal to the natural frequency, this ratio will become 1, and therefore this whole denominator term is going to become 0 when zeta is 0. So you can plug it here and see that if zeta is 0 and this ratio is 1, then essentially the denominator vanishes, leading to this particular term blowing up or becoming infinite in a mathematical sense. So what this tells us is that if we do not have any damping in the system, and our forcing frequency becomes same as the natural frequency of the system, then by magnitude becomes infinite, and this condition is known as resonance condition. So you hear that a lot in vibration and in vibratory fields about resonance and how we should not try not to have resonance. And one of the ways you can see here is that you keep this forcing frequency somewhat distant from the natural frequency, and the second thing you can do is add damping to the system. Now if you see here also, you will see that here the ratio here would be 1, so tan phi would become infinite, which means phi would be 90 degrees or pi by 2. So once again, looking at this equation very carefully, we can see that in the extreme case that you were to design a system such that at certain points your forcing frequency may become equal to the natural frequency, even then you could escape a very bad resonance situation by putting in considerable amounts of damping in the system. So that is what damping does, is that damping mitigates resonance and vibration in general. So that's why damping is actually a positive thing physically, though it may create nuisance in a mathematical sense by complicating our equations. So let us now plot this curve here. So essentially this is often used, we can plot the amplitude here with respect to the natural frequency, and we get curves like this. So when zeta is 0, essentially you can clearly see this function will blow up at the point where the frequency ratio is 1. You get an infinite value of the amplitude. However, as you keep putting in damping, this is mitigated and this also shifts slightly, so you get a slight shift in the peak, and also there is an enormous mitigation in the peak because of the presence of damping. So in many situations we not only have actual damping present in the system, for example, structural damping, material damping, and so on, but we may create some damping device or we may add some damping using some physics based thinking so that we essentially bring this curve down. So, a lot of vibration research and development and work which goes on in companies is aimed at building dampers and trying to create this zeta in the system. So now let's turn to the second part, which is phi. And again, as I mentioned before, at the point where you have this ratio going to 1, you have tan phi as pi by 2. So this is the location tan phi will be pi by 2 or 90 degrees. So essentially here all the curves pass through 90 degree, because whatever your value of zeta, you are still going to get 90 degree at this point here where the frequency ratio is 1. So all these curves will pass through this, but again their directionality when this frequency ratio is not 1 is changed somewhat. So that's the impact here of the damping ratio. So some of the things we learned here, number one is that the presence of damping prevents resonance conditions. So that is something to keep in mind, that damping is very beneficial. And we will see, as far as helicopter dynamics is concerned, damping plays an enormous role in keeping these machines safe and flying and in bringing down vibration levels. The second fact we see is that the forcing frequency should be kept off from the natural frequency. So again, this is a criteria which is followed in most preliminary design practices, is that if you are cognizant of any type of forcing frequency or frequencies, you must ensure that they remain far away from the natural frequencies of the system. And sometimes this is done by actually shifting the natural frequencies of the system by changing values of mass and stiffness. Now, these are the weapons at your disposal essentially to fix vibration problems. You can fiddle around with M and K, which means change the mass and stiffness of the system, or you can try to add damping to the system. Now, as the damping ratio goes up, the sharpness of the resonance condition is mitigated. So that's some point in keeping in mind why we would like to add dampers to the system which are beyond the typical structural dynamic damping provided by the actual materials. And also we may be doing research on materials which have inherently higher damping, such as through smart structures. So now we started with this equation, but many a times we can also start with this equation here, and you will see this in many books. In fact, this is a pretty favorite question in interview situations, is that you may be asked to derive this equation and then you may be asked to get this form. And here the key step is that you divide this equation throughout by m, and then remember that k by m is natural frequency squared. Natural frequency is a fundamental property of the system only dependent on k and m. And the second thing to recall is C is defined as this particular value, that is 2m natural frequency into zeta, by the definition of zeta itself. And therefore, if you remember this equation, then when you get the C by m term, that will simply become 2 into zeta into natural frequency, which is what we have here. And then you can go ahead and solve this, and then you will directly get the equations for amplitude ratio and all in the proper form in terms of the frequencies, natural frequency, and the damping ratio. So now time has come to present the complete solution. So I'm going to present to you the complete solution of the differential equation. So we have the particular integral or the particular solution part, which is the steady state, which we derived just now. So here, as you recall, this is a sine of the forcing frequency into time minus some phase phi, and then the denominator term was given here, and this is the f0, which is again coming from the forcing, and this was the solution we derived in the previous lecture for the spring mass damper system with no forcing. And so again here you had the typical forcing here, typical decay term here, exponential decay term, and you have the sinusoid here, and you have the phase of that particular motion. So now one thing which happens in practice is that because of the presence of damping here, this transient will slowly decay with time depending on the value of damping. If the damping value is higher, this decay will be faster. But in the long run, the steady state is going to survive. So we can come to a philosophical conclusion of this lecture, which is that in the long run, the transient decays and the steady state prevails. So that's a philosophy of structural dynamics. Like we know in finance, they say in the long run, we are all dead. Here we can say in the long run, the transient is dead. So this is the end of lecture 10. I will see you in the next lecture.